Hello, my name is Matthew Northover, and today I will be presenting a short video explanation of the Engineering Mechanics 2 topic of gears. This video will go through a short introduction to gears, followed by an analysis of some important constraints, considerations, and equations that are important in gear analysis. I will then present a simple gear-based problem to help with understanding and revision of this topic. A gear in its simplest form is a toothed machine part that meshes with another toothed section to transmit torque. While they are often circular, an array of shapes can be used for gears for different purposes, some of which I will speak on later in the video. Gears are incredibly useful in our society due to the fact that they allow power to be transferred from one shaft to another with a constant velocity ratio. This velocity ratio is determined using the number of teeth on each gear. A simple example would be two connecting gears. Let's call them Gear A and Gear B. Gear A has 40 teeth, half that of Gear B, which has 80 teeth. The velocity ratio for these two gears would then be 2 to 1, and Gear A would experience 2 revolutions for every revolution of B. I've also included a small picture at the bottom of the slide here to illustrate some of the parts of a gear. Just note the especially important part here, which is the teeth. The uses for gears in today's society are wide and varied, and so only a few examples are being included in this video. Some examples include watches, automobiles, drills, lifts, and countless items of machinery in today's society. And gears are incredibly widespread, and there are many practical applications. However, an in-depth analysis for Engineering Mechanics 2 of the uses of the gears is a little redundant. If you would like to learn more about the uses of gears, though, a simple internet search should yield countless results. There are many differing types of gears used in today's society for many different purposes. The spur gear is the simplest type of gear, shown here. They consist of a circular disc with teeth of the gear parallel to the center of the disc. Gear trains, that is, multiple connecting spur gears, can only be formed with parallel shafts in the case of this gear type. Helical gears, on the other hand, which are the most common gear, do not have teeth set parallel to the center axis and can be therefore run in cross or parallel shaft configurations. Other gear types, such as the bevel gear, the worm gear, and non-circular gears, can be used for other purposes which we will not go into. It should be noted though that this is by no means an exhaustive list, and there are other types of commonly used gears in circulation. These 5 are merely provided as an introduction to some simple types of gears. As I touched on before, the gear ratio is important when conducting any gear-based problem. It is simple to determine the gear ratio of any two connecting, that is, in mesh gears, by comparing the amount of teeth on each. As you can see here, I've put in writing the example that I used earlier of Gear A with 40 teeth, Gear B with 80 teeth, giving us a gear ratio of 1 to 2, A to B. In practice, if two gears are in mesh, the product of speed and teeth is conserved, leaving us with this following formula, where T is teeth number and S is RPM. It is then a simple matter of determining unknowns when presented with a particular problem for gear ratios. Backlash is an important consideration when designing a gear system, and it's a worthwhile consideration in a high complexity gear problem. Although gears can cope with small radial misalignments, a change in direction will generally cause some amount of backlash, that is, time in which the driving gear is applying no force to the driven gear, due to the small amount of space between the trailing face of the driving tooth and the leading tooth of the driven gear. In most cases, this is negligible. However, for machinery requiring high accuracy and precision, some consideration must be made into this problem. I will now show an example of the simple concept shown in the video so far. In this example, multiple gears are meshed together to form a gear train, and we desire to know the overall gear ratio. To do so, we must first determine the gear ratio of each connecting gear. Note that the diagram is not to scale. For Gear A and Gear B, the gear ratio is TA divided by TB. We'll call this R1 equals TA divided by TB. As gear C and gear B here on the same shaft, the gear ratio is 1. The gear ratio for C and D is TC divided by TB. We'll call this R2 equals TC divided by TD. And the overall gear ratio is the product of all the individual gear ratios. That is, I will call this R total equals R1 times 1, which is the gear ratio of RC and RB, multiplied by R2. The number of components in this equation should always equal 1 less than the number of gears in the gear train. And in this case, the 3 components shown for the 4 gears is correct. In putting our initial values into this equation, we obtain a ratio of 3.75. This concludes this short introductory video into gears. I hope it has given you somewhat of an understanding of basic gear concepts and considerations. Combined with other mechanics theory, especially radial motion, complex gear problems can be solved for a variety of purposes. However, the gear ratio remains one of the easiest and most important relationships to find in any such problem.